want to do is relate the equilibrium constant as a function of concentration to the equilibrium constant as a function of pressure. Okay, and we want to derive the equation up there in the overlay. Now, what do we know? We know that Kc is equal to the concentration of the products to their coefficients. And remember, these are not really concentrations, they're relative concentrations. And we use small letters for the coefficients, capital letters to identify chemical species, and these are really unitless, divided by A to the A and B to the B. Now we need to be able to relate concentration to pressure. We can use the ideal gas law as an equation of state. And if we disguise a specific species, then we can say that this relates the partial pressure of species A to the number of particles. And we know that the concentration, remember we use brackets to represent concentrations, even though really it's unitless. We divide by a 1 molar solution, which is equal to the number of particles of A per unit volume, which is equal to the partial pressure of A over RT. Okay? Now what we want to do is we want to substitute here, so for example, since I identified this is the the concentration of A, and we want to substitute this in for here. So now we have Kc is equal to the partial pressure of C over RT to the power of C times the partial pressure of D over RT to the power of D, all divided by the partial pressure of A over RT to the power of A times the partial pressure of B over RT to the power of B. Now we want to factor out the partial pressure terms because we want to get a K sub P. So we have P sub C to the C, P sub D to the D, over P sub A to the A, over P sub B to the B, and this is Kp, okay? And now we have our RT term, and I'm going to put this into two different parts to make this clearer for you to see. And in the numerator, I have the reciprocal RTs. So these really go into the denominator. And I have RT to the C times RT to the D. In the denominator, I have a reciprocal RT, so it really goes up to the numerator. And I have an RT to the A over RT to the B. Now, I'm going to what I have here is the Kp, so I can say this is equal to Kp, and I'm going to keep this in the two parts for a minute, and I'll explain why. So I have RT to the A plus B, and if there had been additional reactants, there would be additional terms. So these are the sum of the powers of all the reactants, because I multiply them, and remember you add the exponents, divided by RT to the C plus D. Now, at this point I can say Kc is equal to Kp times RT to the sum of the coefficients of the reactants minus the coefficients of the products, because if I bring this up, it switches sign. But most books have this written as Kp equals Kc. So this switches the roles of these. So if I say Kp, as is written there, is equal to Kc, now I have in the numerator RT to the C plus D, which is the sum of the coefficients of the products, okay? And then I bring this down. So I'm going to do this in two steps. I have RT over A plus B. And now this becomes equal to Kc RT to the C plus D, adding the coefficients of the products minus A minus B, subtracting the coefficients of the reactants because I brought them up, okay? And the important, and this would equal to Kp P, okay? So hopefully this is clear, and you can simply substitute these in. If on an exam, I often will solve this for the simplest problem, which I might suggest you do, which is AA goes to BB, and then realize that B's are your products and A's are your reactants, and you'll come up with the same form. It's just much quicker to do that, okay? Well, good luck, and I hope this helps.